All right. All right, welcome back to another video on 1MO3, Structure and Property of Material. In this introduction video, I'm going to go a little bit overview about material science and why engineers as well as scientists need to understand material in the first place, which is the core idea of this course. All right, so I want you to pay a little bit of attention on this introduction slide, this title slide. And just spot at different type of household item that you have. Here, there's a chair, there's some kind of basket. This looks like a teapot. And ask yourself, what are they made of? This looks like it's made of yarn or maybe it's bamboo. This looks like some kind of optics fiber. This clearly is a book made out of some kind of paper. This teapot may be made out of metal, maybe made out of ceramics. In this slide, I just want you to think about this and look around your surrounding and just realize that everything that you touch, you see, you smell, you sense are made out of materials. And the course that we're designing for you here is to guide you to appreciate and understand how engineers as well as scientists choose different type of materials for their functions. Okay? So let's just begin and talk about why engineers and scientists care about materials. I hope you will be fortunate enough sometime in your career to be working on some kind of design project. Regardless if you're an engineer or scientist coming together, I think that at one point you will get involved in design. And like I said, depending on what kind of design, but if your design involves a physical object, it's going to be made out of a materials or multiple material at once. Just look at your device, look at your cell phone, your smartphone. The screen is made out of perhaps ceramics or semiconductor, but then the chassis, sorry, the shell as well as the inner component are made out of different materials. And so a device needs to serve a function. And so engineers and scientists need to understand the science behind how each of those components works and works together. And that field that we call this kind of materials is material science. And so you need to understand this in order to actually design any type of devices. Also, you may be working as an engineer and trying to find the right materials for a specific application. And this process is called material selection. And so in this course, we'll focus more on the material science, but we'll also introduce you to a concept called material selection, where you can utilize this concept to design different things. An engineer and scientist basically use this kind of concept to their advantage to create different type of cool design. For example, let's say you are an engineer or scientist and working for NASA, and you are creating the next coolest spacesuit. You need to understand the property, the function of this spacesuit, and you need to understand each of the components serve different function. And that's the reason why the spaceship are not made out of one single materials. They all need to serve different type of purposes. So maybe the shield area need to be optically transparent, but also need to be able to withstand the pressure differential in the outer space. So what kind of polymer or what kind of glass would be good for this kind of materials? And then, well, for area that you don't need optical transparency, maybe you can use other type of materials that are more flexible, but still withstand that pressure differential. You may be a structural engineer, or you may be working on designing sustainability challenge. What kind of materials should I be using on a turbine blade or turbine or a windmill? What do I care? Do I care about strength? Do I care about ductility? Do I care about stiffnesses? Do I care about cost? Do I care about weight saving? That depends on your design, and this will lead to what we call material selection, selecting the right material for your particular application. For example, looking at this particular car chassis, it's actually made out of metal, but within metal, there's still a lot of different type of alloys. You might think that it's all made of steel. This is actually a car chassis diagram of a Toyota Corolla, I think. And so if you look at that, you realize that actually it's made of various type of grade of steel. So why engineer and scientists choose to use different type of grade of steel for each of these components? There must be a reason behind it, and that's material science. For example, this pillar, I think it's called the A pillar, need to be very strong because they need to withstand the weight in case of a car rolling over. So this needs to be very strong. End up we're using ultra high strength steel. One of the reasons we use ultra high strength steel rather than other type of alloy is also because it's low cost in comparison. In the frontal area of this car, it may be subject to other type of accident, and you may want this area to crumble. And so we decided to, in this particular case, we decided to use aluminum alloy to actually design this kind of bumper structure because they can crush better than high strength steel. And so you can hopefully, by just looking at this diagram, you can appreciate that engineers and scientists are really thinking together of choosing the right material for their particular application. So, like I said, this course will talk about two types of design philosophy in material science. The first one is material selection. In fact, we will actually introduce you to a software called ANSYS Grantor. And in this software, you can actually graphically look at a database of approximately 6,000 type of engineering materials as well as natural materials that is currently recorded in humankind. And we'll use this software to help you to design the right material for your application. So you can think of each of this material, it's like a character in your video games that maybe you're playing. And if you go into a video game website, you can see that this character has different type of strength and weaknesses. Well, material also have that. And in this particular software, it has a database of showing you different type of materials, what's their property, which are the strength and weaknesses. And by showing you that, we can create what we call the material property space. This is basically a design space of different combination of material properties. And graphically, I want to show you a 2D version. So we have property 1 and property 2. Let's say you are designing a problem, a hypothetical problem, where property 1 is desirable and property 2, you actually want to minimize it. So then we are going to be asking, okay, well, which material is best? Well, we need to draw a ratio. So maybe ratio of property 1 over property 2. And if we look at 4 different type of hypothetical materials, let's say in this design space, we have material A, material B, material C, and material D. They are located at different spots, and so they have different combination of property 1 and property 2. Well, if you want to maximize property 1 and minimize property 2, you might say that this blue circle is a better material, whereas the rest of the material are worse. But how do we evaluate that? That's material selection process. We'll go into more depth about that. Now, what happens if you look at this graph and you realize, okay, the 6,000 materials that we have in the database does not have the property that I want. So let's say you want to maximize property 1 and minimize property 2. So this blue circle is good, but you want something better. You want something that have a higher ratio of property 1 versus property 2. Do we give up, or do we just use the blue circle? This comes to the next design philosophy of material science, and it's how to expand the material property chart. And so, like we said earlier, we need to understand the property of the materials. And if we understand that, we can draw this kind of material property chart. And after that, we can select the right materials. But if we want something better, we might want to expand this property chart. By expanding it, other engineer and designer have a bigger options of a pool of material to choose for their particular design. So in the ideal case, what we want is actually a full map, a map that actually full of materials, where filled up every single spot of combination of property 1 and property 2, so that people can choose the right material for their application. How do we do that? How do we expand this material property space? That process is through what we call process structural property relationship. What we're doing here is we're using some kind of material processing, which we'll talk a little bit more about it, to manipulate and change material property of an existing material. And by doing that, we expand the property chart. So to give you an example of how material properties actually expand throughout the history, we can look at this chart, which is date of, on the x-axis date, and on the right axis is relative importance of materials. So in the very early age, we are talking about Stone Age, majority of the material are actually made out of ceramics and glass. We have some polymer, but at this time we don't call it polymer, we call it natural materials. We have bone, skin, fiber, so maybe a lot of material made out of leather, right? Straw is actually a composite materials, but a lot of this material at this time are just basically you grab whatever is available created by nature. So all these material at this point are natural materials. At this point, actually, we have metal that are within the material property space, and we can use that. However, if we look at the material property space, so let's say here on the x-axis, we draw density. On y-axis, we draw strength. So let's say at this point, we were trying to find the right building material to create structures. We will find that gold are actually weaker than the existing material that are available at this time. And that's the reason why gold were never used to create weapons. They were used to create jewelry. They were rare, they were expensive to find, and they were not structurally sounder compared to bone as well as other ceramics material. So this is Stone Age. As we discover chemistry as well as different type of materials as human civilization evolve, we start to see that new material evolve coming out. And at this point, when we look at Bronze Age, we can see there is a huge boom of application coming out from metals at this point. That's the reason because iron and brass are now stronger than ceramics in terms of, if you just look at the y-axis of this graph. And so at this point, we start to find that iron and brass is stronger than most of the ceramics material and tougher than them. Whereas ceramics may be strong, but they are very easy to chip, which is called brittle. And so this is the reason why Bronze Age and Iron Age arise, creating all this kind of medieval weapon that we can see in museum that we appreciate now. As time moves on, we start to see another boom, and this is called the Steel Age. And we can see that at this time, humans are starting to realize maybe we shouldn't be just using iron in its raw form, but rather we should be using it with an alloying form. So what is alloying? Alloying, for example, what steel is we put carbon impurity into steel. And by doing that, we actually strengthen the steel. And that's the reason why you see an increase in strength level in this metal again. And this leads to the huge boom of 1900, where pretty much everything were made out of steel at that point in engineering applications. Railways, bridges, structures, even buildings were made out of steel at that point. At this point, we're starting to have a new development or chemistry discovery of polymer. We have figured out how to actually turn monomers into polymerized form to create these soft material that are relatively durable for day-to-day application. And by doing that, we have created a polymer age where we start to use polymer for various type of application, maybe shell of a structure, say a telephone cases, or it could be used to create nylon fiber for socks or stocking. So clothing material were created by these kind of polymer. And then recently, in the last maybe 18 years, we start to actually realize there's a new strategy to create this kind of new material. How to expand this is by combining existing materials and create what we call composite or hybrid materials. And so here we can see that at this point, we're starting to actually have a new boom of materials that is available. And we can see these materials. So we have natural material, polymer, composite, ceramics, and metal all works together to fill up this material property space. In this case, it's strength versus density. You can imagine that if I change the y-axis and x-axis to other type of material property, we'll see a different type of graph. And the idea is we want to expand this as much as possible so that other designer, engineers, and scientists can pick the right material for their application. So here's an example of how we actually use this material expansion to improve one application. So information are important. I am a strong advocate about education, and I care about how information are being distributed. Well, and humans are unique in doing that. And so this is the proudest invention that we have ever created, in my opinion. And so if you look at that, material have actually driven the way we actually store information. At the very, very early Stone Age, we only have natural materials. So we use stone, we use bamboo to create information where we can store. But then we start to invent new materials. This is a type of composite. Paper is a composite utilizing natural fibers, and they're far more efficient and easier to actually store information, and lighter than what is existing at the time compared to stone and bamboo. Well, as we evolve, as time goes on, we start to develop metal as well, and we found that you can actually create this kind of machinery that duplicate paper and distribute information throughout the globe using printing press. And then later on, we have figured out how to actually utilize glass to use to create vacuum tubes. And by doing that, we have created the first computer. And fast forward to today, we have discovered semiconductor, such as silicon chips, to actually understand their unique property, electrical property. And by doing that, we have created what we call MOSFET, and we can put trillions of MOSFET diodes inside these kind of semiconductor chips. And that's the reason why we have powerful computer that can play chess better than humans. So let's give you an example of how structure and property are related together. And so a concept that you may see from material scientists that we often draw is this tetrahedron. We call it material property tetrahedron, or we call it property, structure, process, structure, property, and performance relationship. In this particular course, we'll be focusing more on the structure and property relationship. And so to give you an example, here is a metal, what kind of structure that we have. And metal are made out of atoms. And in fact, anything that is physical is made out of atoms. And so in particular, metal are atoms with metallic bonds. And so the structure at the atomic level, we call it microstructure. And on the right-hand side of this graph, you can see different type of property. And so depending on how atoms are arranged together, how they're packed, and they would be also packed in a way that have some kind of defects. And these kind of structure, the arrangement, spatial arrangement of this atom will have a huge impact of the property. After that, the structure of this particular device will also have different type of property. For example, surface roughness, micro cracks, or larger cracks, and maybe even poorly designed structure that have stress concentration can have an effect on the material property. So to give you an example, you may have seen a TV show called How Stuff Made, and you may have seen how an aluminum can are made. Well, an aluminum obviously will first start off with the process of casting, and then after that it goes through rolling, and then it's been deep drawn, and then it's turned into an aluminum can. And an aluminum can need to withstand the pressure of the CO2 inside this beverage. And so what is going on in this process? It actually can change two things. You may think that what we're doing here is changing the shape of that metal from a very thick piece of slab aluminum into a thin sheet. You're correct, but deep inside, if you look at it using a microscope, there's a lot more going on. And this is what we call process-structure relationship. So for example, during the continued casting of that aluminum, atoms will slow down and attract to each other and forming what we call crystal. So for example, you have learned that in your high school that liquid have a larger atomic spacing. And as you cool it down to a, let's say, closer to room temperature, then the atom will want to actually pack together and become what we call crystal by lowering the Gibbs free energy. And so if you look at it at a more macroscopic level, what you'll see is that, let's imagine these are all aluminum liquid, and inside we have these individual crystal are forming rather randomly at first, but they will grow. And as they grow bigger and bigger, they eventually collide with each other and forming these boundaries. And these are called grain boundary. And so you can imagine, depending on how fast you cool these materials, there's a different growth rate on this crystal, and the crystal size will be different depending on the growth rate. After that, you're actually going to be cold rolling this aluminum sheet or slab. And by doing that, you're thinning this sheet, but at the same time, you're also making a change to the atomic structure because you're deforming this crystal. These crystals are now more elongated. And you can imagine each of this crystal also involve trillions or even more atom in there. And there's also a more microscopic level of changes that we'll talk more about it in this course. But in short, all these structure, what we call microstructure, can have an effect on the material property and thereby in changing the performance of the materials. So in summary, in this lecture, you have learned that there are two design philosophy in material science. The first one is to select the right materials, we call material selection. And if the material is not available at that time, then what you can do is you can expand the material property chart by using the strategy we call structural property relationship, as shown in this slide. Thank you very much.